Hey everyone. How are you guys doing? All right. I just returned your exams. I was very pleased with how you guys did. It was quite a few perfect scores and quite a few people who even got the bonus as well. So I'm really happy to see that. If you felt like you didn't do as well as you hoped, just learn, do your best to learn these questions. This full score is 9. It was out of 9 points. Yeah, do your best to learn these questions. If you miss some sort of question or some concept, you can always message me, and maybe we could schedule a retake. That's only something you would look for if you got below a 6 or so. Okay. So I'm going to shift gears a little bit. We did some stuff with random variables. I do want to ask, did you guys have any questions from the homework?
I don't really remember what it's called because I haven't looked at it in a bit, but the very last con assignment was a bit confusing.
Okay, yeah. Let me take a look. Yeah, cool. Quentin, the next section that I want to do, I want to show you guys a little bit of. I want to get into a little bit of statistics, kind of talking about analyzing data and using something called the z-score table. And then later, I do want to go back to random variables and expectation and that stuff. So we'll do a little change of gears. So let me see here. Classes, multiple courses here. Oh, I have a new student. Okay, update assignments. Let's see here. Assignments, manage. Was it? Let me see. Scores. Okay. Alex, do you remember if it was constructing probability distribution, probability models, probability with discrete random?
Probability and density curves, I think.
Okay, let me see that.
Oh, sorry, transforming random variables. I was looking at the wrong one.
Okay, got it. Okay, so this is yeah, I want to talk a little bit about statistics today to introduce the idea of standard deviation because I didn't get to introduce that yet. But let me just share the screen here. Do you remember which question? Was it just one question? Oh, no, there's 4 questions.
Concept I didn't really get.
Oh, okay. Yeah, so the okay. So this is actually a really important idea, and the thing is, I didn't show you guys what standard deviation is, unfortunately. So, but Alex, kind of in a quick minute here, the idea of transforming random variables, one way you can think of it is, like dice, for example, right? dice, they range from 1, 2, 3, 4, 5, 6. And what's the expected value of a dice roll? What's the average dice roll going to be? Do you remember this one?
It's somewhere in my notes, but I don't have it off the top of my head.
Oh, yeah. How could you think of it from off the top of your head, if you forgot it? What is it? If you roll 6 dice, let's say, or 60 dice, you'd expect about 10 of each. So how do you quickly find let's say, the average of the numbers 1 through 6?
Well, like finding an average, add all 1, 2, 3, 4, 5, 6 together, and then divide by 6.
Exactly. And for dice, because they're evenly spaced, there's a shortcut to do it. You don't actually need to add them all up. Because they're all evenly spaced, it's going to be the one right in the middle of 1 and 6, which is, Lacha, you're right, it's 3.5. So that's the expected value. If you transform the dice, so rather than having labels 1 through 6, a transformation just assigns the outcomes different numbers. So what if we transform the random variable, like the dice outcome, by tripling the number? What would that do to the expected value? So now instead of the dice roll having 1 through 6, it has the numbers 3, 6, 9, 12, 15, 18. So it goes 3 through 18. What would the expected value be in this case? Oh, I should draw this. Not exactly 9, but close. Nice, Kieran, yeah, exactly, it would be 10.5. So if X is a dice roll, that means X could be represented as, and 3X could be a dice with labels 3, 6, 9, all the way to 18. Then if you do the table, here's X, this would be 3X. This is the probability of little x. Then you do 1, 2, 3, 4, 5, 6. This is 1, 6, 1, 6, 1, 6, and so forth. And this would be 3, 6, 9, 12, 15, 18. So clearly, if you take a random variable and you just multiply it by something, the expected value of the transformed random variable, kind of the relabeled one, so the expected value of 3x, well, you can just take the 3 out. This is just going to be the 3 times the original expected value. I don't know why I'm doing it like that. The other thing you can do with and so in this case, it was 3 times 3.5, which would be 10.5. Now, the other thing we can do with the random variable to transform it in a simple, really simple way is we can also not only multiply all the numbers by a constant, but we can also shift everything. So instead of labeling the dice 3, 6, 9, 18, imagine we labeled it 103, 106, 109, and 118. So that would be a new random variable, 3x plus 100. And this is a really simple type of transformation where you just multiply by something and you add a constant. What would the expected value of this random variable be? Nice, Quentin. Yes, it would be and Karen also. It would just be 110, 110.5. So that's a nice idea that will kind of it's a really general idea that once you understand the dice roll, you basically understand a lot of similar distributions, even if they don't happen to be 1 through 6, but maybe 6 numbers that are evenly spaced located somewhere along the number line. And then you can talk to me about the expectation because you know the original expectation and you can easily calculate the new one if you know how the random variable got transformed. Alex, did that clear up a little bit of what they're asking about here?
Yeah.
The thing that I didn't mention, though, is the thing with the standard deviation. Let me think here. Yeah, okay. I'm going to talk about variance and standard deviation now, and then yeah, I'll talk about that now, and then next class we'll talk about get into actually talking about statistics and how to apply some of these ideas for using actual data and using the bell curve. So just a show of hands before I start this discussion. Hit yes if you have ever calculated the standard deviation of a data set. And it's not really important if you have or haven't. It just and hit no if you have never done that. Yeah, it was in the con problem. Yeah, but I didn't talk about it in the class. Okay, so we're gonna start from scratch. We're gonna so the standard deviation And by the way, every time you see the word distribution, you can always think it's kind of synonymous with random variable. Okay, so we've encountered a few random variables so far. We've encountered continuous random variables or continuous distributions and discrete random variables like rolling a die. We've also seen random variables. I haven't maybe explicitly talked about them as random variables, but like, oh yeah, we did. We saw binomial random variables where it has to do with how many, like when Shaq is taking 10 free throws, what's the chance that he makes 5 shots or 4 shots or 3 shots? So we've seen a few different examples of random variables. And one thing that we can talk about for each random variable is we can make this table and we can multiply together the outcome times the probability of the outcome, like this, and just add them all up. And that gives us something called the expected value. And that's a nice idea because it tells you on average over and over, if you were to repeat that same random variable or draw something from that same distribution, on average, what do you get out? But there's another important random variable, another important quantity associated to a random variable called the standard, called the variance, and also something related to it called the standard deviation. So to illustrate the idea, why is kind of something that might be relevant to think about when you're describing a distribution. And by the way, we use expectation to sort of describe a data set or describe a probability distribution. So what do you guys think about these two statements? This is just some motivation why we talk about standard deviation or spread of a distribution. I could say, oops. So here's statement one. The average salary, and this is not maybe not a true statement, but I'll ask you to interpret it and kind of say the average salary at McDonald's and Google, or the average salaries are both 100,000. Therefore, a job at Google is likely to pay just as well the same as a job at Mickey D's. By the way, I don't know if you guys saw this, but McDonald's has a bundle going on, a bundle deal. You can get like a lot of nuggets and some fries or something for like, I think 18 bucks. I don't even know if it's actually a great deal or not, but I just saw that. Okay, so any objections, any explanations why this might be true and why it might be misleading?
It could be misleading because you don't know what the lowest and the highest incomes are. Like Google could have a really, really low income, but it also could have one that's way higher. The average, and same with McDonald's.
Yeah, and so like kind of how could, based on what you sort of know about McDonald's and Google, maybe, yeah. What would you say is an important thing to? So Alex, you said the highest and lowest at each job is important to describe, right?
Yeah.
I agree. Can anyone kind of give an explanation of maybe this statement is actually not true, like the average salaries are both 100K, but how could that actually happen? Because we know, at McDonald's, most employees there are getting minimum wage, unless you're a manager at the branch. So how could it happen that the salary would be 100K, the average salary?
A few very wealthy like CEOs or managers would be upweighting to offset the fact that the vast majority of them are making under 100,000.
Exactly. So Alex and Quentin have the right idea there, that there could be some outliers, like the CEO could be making 100 million a year, something crazy, and everybody else kind of like maybe not McDonald's maybe McDonald's isn't the best example, but maybe like Amazon is a better example, you know. And maybe at Google, even though at Google, the people at the top also make way more than the people like that are starting out. But generally, like at Google, you know, if you're starting as an engineer at Google, you're going to get paid a very competitive salary. So it's feasible that the distributions might both have an average of 100, but if you were to draw a histogram of the salaries, and keep in mind, when I say histogram, it's very similar to a probability distribution, right? Because it kind of shows you the likelihood of getting a certain salary. So this is the salary. This is the likelihood. This is the percent of people that have that. So this could be at Google. So maybe everybody is like, you know, if you put it in buckets, maybe like everybody is around like 100K or something like that. But maybe at McDonald's, you have a lot of people that are making like minimum wage, which maybe put you at 40K annual or something like that. So that would be most people making around there. Some people around that. But then one guy all the way out there is making like, you know, 100 million. Oops. So, the idea here is that just telling somebody the average or the expected value of a random variable, you might miss some important information that actually tells you the distribution. Now we'll talk later about how you can sort of, this is actually not really the best example of what I'm trying to illustrate. But because technically, if you ever encounter a data set like this, you would probably say, okay, well, let's not include the outlier because that's somehow going to throw off our data set. And it's not representative of the overall employees at McDonald's. But the idea is that there's more variation. There's more variation. So this is at McDonald's. So there's more variation here. Versus the salaries at Google. It's that outlier that creates a lot of variation in the data. So it's more spread out, or more spread out. More spread out. Okay. So I'll give you the formula for calculating standard deviation of a data set. So, and then we'll talk about kind of, I'll give you a justification of what this formula actually represents. But first, I'll just kind of describe what the formula is. So let mu be equal to the So first we're going to do standard deviation for a data set, and then we'll do later standard deviation variance for a distribution. So if we have a data set, x1, x2, xn. So this could be like, for example, the different salaries of n people. These are little x's. And so we just went up to, like, let's say 1,000 people, n is equal to 1,000, and we got 1,000 different numbers for their salaries. We say mu, or I'm going to say actually not mu, I'm going to say x bar is the average of the data set. This is the average of the data set. This is going to be equal to the sum of all the x's. So sum over x sub I is just an index. I will technically range from I equals 1 to n. And then we divide by n. So this is just a fancy formula for saying add up all the numbers, add up all your data points, add up all the salaries, and divide by how many people there are. And we call that by x bar. And keep in mind, this is a data set. This is not exactly a distribution. You could think of it as a distribution where like the likelihood of each number is 1 over n, but we're just thinking of this as a set of numbers. Okay. So the standard deviation, which we call S, and later we're going to call it, well, maybe I'll call it sigma. So the standard deviation. I'm going to give you the formula for the, I'm going to call it S here, and it's a little bit, yeah. But sometimes when it's from a data set, we call it S. When it's from a random variable, we call it sigma. So sometimes sigma. And I'll explain later why it's S versus sigma, but it's not a big issue right now. So the standard deviation is the sample standard deviation. That's why we call it. The sample standard deviation is equal to the following formula. You express, because we want to get a sense of how spread out things are from the average. What does it say before the S? It says standard, yeah, let me write it out better. I shouldn't. Sample standard deviation. And what we're doing here, the formula here applies when you just collect some random data and you want to measure its average and you want to measure its how spread out it is. When you have a random variable where everything is like completely known, the calculation is similar but a little bit different. But for now, we're just going to say, imagine you're collecting some data, and we call that a sample of data. And when we get into the statistics, we'll dig in a little bit deeper on these different the distinctions. But here's what you do: we want to measure how spread out everybody's salary is. So what we do for each person is we say, okay, take your salary and tell me how far away you are from the average salary. Now, one thing you can do is you don't care if somebody's above the average or below the average. We just want to know like how far away they are from the average. So what can we do to xi minus x bar to just get a sense of how far away something is? Yeah, a nice one. Yeah, you can put absolute value in it. So that turns out to be actually, or you could square it. So there is one measure of the standard deviation. I forgot what it's called, but where people take the absolute value. But we're not going to do that. It turns out that a very useful thing to do, like you suggest, is to just square this number. And for each data point, that tells you, like, gives you a sense, an absolute value sense, where the square of how far away you are from the average. And you're essentially going to add these all together. So we're going to put sum over I equals 1 to n. So go to every data point, see how far it is from the average, square each of those distances from the average, add them all together, and then kind of average it out. And there's this weird number here, n minus 1. But you can just think of this overall as like dividing by n. It's very similar to dividing by n. And then take the square root of everything. So this sort of complicated looking formula, but hopefully not too difficult to see what it's actually measuring. This is what we call the standard deviation. Let's just do it really quickly with a simple data set, okay? So look at the data set. So this is, we collected data, we got the numbers 1, 3, and 5.
Why is it n minus 1 instead of just n?
Okay, that's a really good question. And when I first learned this, that tripped me up for a long time. It's like, why shouldn't I just take the average of how spread out everybody is, and then you can take the square root if you want. So it has to do with something called the bias of an estimator. Little lowercase s doesn't. The idea is when you pick things, when you ask like 1,000 people their salary, you're assuming in our formula we're trying to we're drawing those 1,000 people from a sample. We're not actually getting them from everybody at the company. Or if you were to like measure the height of 10 giraffes, and you're trying to extrapolate from that, like in statistics, you often take a sample and you try to extrapolate from that sample some knowledge about the general population. And we'll get into this next week, or sorry, we'll get into this on Thursday. The idea is that the general population has some true probability distribution, but we don't have access to it, right? I can't go, it's not feasible for me to go out and measure every giraffe. I might not even be able to find every giraffe. Maybe for the employees at Google, this is not the best example because you can technically have a spreadsheet that tells you how much every employee at Google makes. But whenever you're taking a sample from an overall population where you don't have the information, entire information about, what you're calculating here, in particular, X bar and S, these are what we call statistics. Because do you agree that if I like pick a different set of like giraffes, just a different sample of giraffes, X bar and S could change depending on which set of giraffes I picked. So so X bar is like the average of my sample, but it's not necessarily the average of the entire population. And S is the standard deviation of my sample, but it's not really necessarily the standard deviation of my entire population. Exactly. So this n minus 1, it does something when you compute this, when you compute the estimate of the standard deviation this way, you, for some reason, you include, it creates a sort of artifact that always like overestimates the standard deviation a little bit. So you, instead of dividing by n, you multiply, sorry, it always underestimates it. So you multiply by n over n minus 1 to kind of adjust it back to a slightly better off estimate. The idea is that when n is large enough, it's barely any difference. But this is what the sample standard deviation is something we call a bias estimator. So you have to multiply by some factor to make it make it unbiased. Basically, we can go over that a little bit later in the course. This was something that I didn't know for when I first took statistics. I don't think my teacher even actually knew why, and then I only figured it out later when I took stats again in college. But yeah, but that's a very good question. So let's just really quickly calculate the standard deviation of these two sets that have the same. These guys have the same average. So here x bar is equal to 3, and over here x bar is also equal to 3. Okay, so what do you guys get for the standard deviation for the first number? I'm going to put everything in a square root. I'm going to write s equals, put the whole thing in a square root, divided by 3 minus 1. The average is 3, and so it'll be negative 2 squared plus 0 squared plus negative 2 squared. That's going to be 8 over 2, which is equal to square root of 4, which is just 2. All right, and let me know what you guys got for the next one. Nice. I think that's right. I'll wait for a few more answers. Is the first one, is everyone okay? Give me a yes if you're okay with how I did calculated the first one. Great, awesome. Nice, Alex. You got it. And later I'll show you guys, maybe in next class, maybe later today, I'll show you how you can, because this is kind of tedious, obviously, to do if you have a lot of numbers. Nice, Olivia. Excellent. So several students got 1. So in this case, it would be s equals square root of negative 1 squared plus 0 squared plus 1 squared over 3 minus 1, because there's 3 numbers. And this is just going to be square root of 2 over 2, which just happens to be equal to 1. Okay. And this is kind of nice because you can have this interpretation that, okay, these numbers are evenly, like 2 and 4 are both 1 step away from 3. And so 3 is kind of the middle. And in the other case, 1, 3, 5, the distance is twice as far. Every number is twice as far away from the middle. So the standard deviation in that case got doubled. All right. So that's kind of the basics of standard deviation. I want to show you guys something that you might not have seen. Some of you might have seen it before, to show you a different interpretation of standard deviation and how it connects to like what we just did. But any questions? So just thumbs up if you understood both calculations and kind of have a sense of what standard deviation is measuring. Awesome. And yeah, if you hopefully you agree that if you were to take the standard deviation of Google, you know might get like roughly, it tells you how spread out the number generally tells you like where most, like the range of how far away most people are from average. So maybe you get something like $15,000. So you'd say like uh, um, and you know, you're probably hearing a lot of this today about like margin of error and stuff like that. Standard deviation is very closely related to the idea of margin of error. Um, but for the McDonald's distribution, the data points that are way out here, this data point, when you subtract it from the average and you square it, it gets really, really big. So it really throws off your standard deviation. So you're going to have a much higher standard deviation if you have some data points that are really spread out. And I'm going to shift gears a little bit and just show you guys. So I'm going to show you guys something from 3 dimensions that if you've never seen before, I'm happy that I get to show it to you. But if you have, you can also message me. So imagine you have a box from Amazon, a rectangular prism. And this is in 3D, so we have something like that, and go like that, and go like that. Okay, we have our 3D box, and imagine I want to know if I have a piece of string, and I go from the inside of the box from one corner all the way to the other corner, how much string do I need I'm just going to do all dotted. How much string do I need to go from one corner to the other? And the dimensions of this box are going to be, let's say, 3. No, let's do something. Let's do like maybe even bigger. 5, 3, and 2. Okay. So the question is, how long is the red string? And if you've never seen this before, well, message me if you've seen it before. And if you've never seen it before, I want to give you a little bit of time. Yeah, Quentin, it's a few steps away from what we just learned, but I'll tie back to what we learned at the end. But yeah, for now, you can think of this as a completely different problem. And some of you might have seen this before. It's something you learn sometimes if you're doing like SAT prep, or at least the old SAT had it. But I'll give you guys a little bit of time to think about it. And if anyone has a good idea to share, you can message me. And maybe I'll ask you to. Oh, Kieran, you did? Really? Nice. How far did the project go? Or what did you?
It was just a writing thing I did. We were given the opportunity to write whatever we wanted, and I just did a bunch of like little proofs with like sorts of formulas and stuff. And one of the ones that I wanted to do was proving the Pythagorean theorem, and this kind of evolved from that.
Awesome, excellent, very good. Okay, so I'll give you guys a few minutes to think about it, because if you've never seen it before, Kieran gave a very good idea here. This is related to the Pythagorean theorem, but it's not the usual Pythagorean theorem. It's a little bit, as he said, like a little bit extended or expanded. But if you know the Pythagorean theorem, then you can solve this. So I'm going to give a chance to everyone for about, like, let's say the next 10 minutes or so, or 5 to 10 minutes to think about it. Message me if you have some ideas, and I'll message you back. And if you have some drawings also, you can you can share the file or whatever. Awesome. Oh, for the answer, you can leave the answer as a square root. So leave it as an exact answer. Don't put it into decimals. Well, Nice. Awesome. Nice. I'm happy a lot of you are seeing the visualization. There's you just have to see one thing, and then you can, once you see that one idea, you can see it. Oh, by the way, once you see that idea, come up with a general formula. Instead of 2, 3, 5, like those are just numbers I made up. Use the letters A, B, C to figure out the red length, which is equal to D. So once you have that, see if you can come up with a nice formula. Oh, wait, that's right. Oh, wait a second, you don't mean, no, you don't mean the last part though. So those of you that said square root 29 times something, I like how you're thinking. You're very close, but okay. Anyone who feels that they got the idea, maybe Lacha, do you want to kind of try to annotate on my picture? I realized my picture, let me redraw my picture a little bit so maybe you can annotate on it.
Sure, I can annotate on that one too.
Yeah, I think the diagonal that you want to draw is going to be a little bit hard to see. So let me just draw it. I think how to best draw it here. If I draw it like this, it might be a little bit easier. Oh, this is 2, 5, and 3. So I'm just redrawing this thing, and then down here is these guys, and over here is the red line that we want. Goes through. Oh, I guess that's even worse. I don't know. No. What am I doing? That's not too bad. Do you guys see that this? I'm going to draw this diagonal instead. So this goes through the shape. Okay, Lacha, go ahead. If you feel comfortable to draw, you can annotate on my picture.
Sure. So the way that I thought about it is that we can find the third length of a triangle, like a diagonal, just by doing a squared plus b squared equals c squared. But we can't find the red line because we're missing a piece of information, which is this cross section right here. And to find that, we can just do the Pythagorean theorem. So 5 squared, I'm not going to write that out, but 5 squared plus 2 squared plus that purple line squared, which ends up being, I think 30, no wait. 5 squared plus 2 squared is 29. So then we can take that and then do the Pythagorean theorem again with this line now to find the red line. So we can do 29 plus 3 squared, which is 9, is going to be equal to our answer squared. So that'll be 38. So the length of the red line is going to be the square root of 38, which is some big decimal.
Awesome. And I'm just going to draw in. Thank you, Lasha. That was great. I'm just going to draw in here, just so that everyone is careful with it. The 29 is that base diagonal squared. So therefore, the base diagonal is square root of 29. And then when you plug it into the Pythagorean theorem for that, I think of that shape that you drew there as like a college flag. You guys know like the flags people have in colleges? They like, or like some sort of long flag like that.
Yeah, I skipped the step of like square rooting the 29 and then squaring it again. I just kept it all the way through.
Excellent, good. So just make sure that everyone who's watching this, that there's a step of square rooting and then squaring again, but it just stays as 29. Okay, and then Lasha, what is the final formula that you got? If instead of 2, 5, 3, I just picked randomly. If we did A, B, C, and we wanted to find the red line, what formula did you get at the end?
The square root of a squared plus b squared plus c squared. I have a squared and b squared in parentheses, but I don't think it matters.
It doesn't, right? In the beginning it did because you took the square root of it, but then you square it, so that square root goes away, and it's just a squared plus b squared plus c squared. So I'm just gonna clear your annotations here, but that was awesome. Are there any questions on Lasha's steps?
Sorry, what was the final equation? A squared plus b squared plus c squared equals d squared?
Yes, exactly.
If you added a dimension, could you just add another variable again?
Exactly.
Interesting.
And so we'll see a few nice things here. Let me draw better kind of how Lasha did it here. I like that you drew that. So we know that this is going to be square root of 29 because we have 2 squared plus 5 squared equals 29. And then the last one is square root 29 squared plus 3 squared equals to, this is equal to d squared, because we have that last part, and this is going to be 38. And if you instead just go through the same pattern with a, b, and c, you get this nice formula that d squared equals a squared plus b squared, square rooted squared, it goes away. So you can put it in parentheses if you want, plus c squared.
And then Kevin's in the waiting room right now. He got kicked out by computer stuff.
Okay, thanks. Okay, and so in particular, we find this formula. This is called the 3D Pythagorean theorem. It gives you a way to find the distance between 2 points in 3 dimensions if you know their width, their height, and their distance, their width, the length, and the height that they are from each other. Then you can figure out the distance, the direct distance in 3D space. So we get this nice formula that the distance equals square root of a squared plus b squared plus c squared. This is how far apart this is how far apart how you can measure distance in 3 dimensions. In 2 dimensions, we know that the distance is equal to, or we have the distance is equal to a squared, square root of a squared plus b squared. Or instead of the hypotenuse c, I'm just using it as the distance. And by the way, do you guys know how these formulas connect to the regular distance formula? If instead I had, here I'm giving you the lengths of the rectangles, but what if I told you 2 points in 3D? So let's say I have x1, y1, z1. This is a point floating in 3D space right here. And then I have another point, x2, y2, z2. Do you guys see how this gives you what you call the distance formula in coordinates? Right? For 2 dimensions, it's you just replace the, in 2 dimensions, if you have x1 here, y1, and x2, y2, you get a little triangle, or you get like a little rectangle if you want, and you can figure out the distance here by using Pythagorean theorem. You just replace a with square root of x2 minus x1 squared plus y2 minus y1 squared. And in 3D, it's the same thing, except what's the only difference going to be in 3D? What else do we have to add in to get the 3-dimensional distance formula? What's the last part that I want to add in there? So I'm accounting for the difference in the x coordinates squared, the difference in the y coordinates squared, but I also want to include the change in height of the different points squared. So this gives you a way to measure the distance of between two points in different numbers of coordinates. And now we're going to do something a little bit weird. So first we're going to do something really easy, and then we're going to do something that you can't even visualize. So what do you guys think? What do we know if you have 2 points in, this isn't, we talked about 2-dimensional distance, 1-dimensional distance. What is the formula to find, if you're going to continue with the same pattern, what is the formula used to figure out the distance between 2 points in 1 dimension?
X minus x2, absolute value.
That's right. That's one way to do it. Just take subtract them and do the absolute value. But according to the pattern, what's another way to do it?
Square it and then take the square root.
Yes. So that's why if you ever do some later courses and they talk about distance, they use absolute value to measure distance as well. So absolute value isn't just something that makes something positive or negative. It really comes from squaring and square rooting a number, which gives you the positive, the magnitude of it. So I just really like that fact. I think it's a neat fact because it just fits in with the pattern so well. But it's really obvious. It's, or maybe I like it because it's so obvious. I don't know. Not obvious, but something that we all learned from so early on, but it's a nice extension. So that's the 1-dimensional version. Now, what if we have, how should you interpret, 0 dimensions? Quentin, that's a good question. 0 dimensions, let's see. Technically, I think that would be 0, right? Because you're not adding anything. There's nothing to square. So the thing inside would just be square root of 0. So, and every point, I never thought about that one, but I think, you know, if you're in 0 dimensions, your entire universe is in 1 point. So everything is 0 distance from itself. But what about 4 dimensions? How do we think, what does 4 dimensions mean? Can we visualize 4 dimensions? It's just another letter, it's just another coordinate. So 1 dimension is just 1 number, 2 dimensions is 2 numbers, 3 dimensions is 3 numbers, 3 coordinates. 4 dimensions, there's different ways to like think about 4 dimensions. You can do, you can represent it as regular 3D space, but then at each point in 3D space, you give it a color or a temperature. So that way, to each point in 3D space, you have 4 numbers. You have its position and you have its temperature. Another thing people do is they think of it 4 dimensions as a movie where you have like your position and then you also have another parameter, another coordinate that tells you the time. You can make it V. Yeah, but yes, we could just introduce another letter. We don't, as mathematicians, we don't need to think necessarily about the best way to interpret 4 dimensions. We can just say, well, it's just a list of 4 numbers. There's nothing esoteric about it. It's just as, you know, you have a list of 3 numbers, you can have a list of 4 numbers. Quentin, that is one interpretation for sure. You can animate, the 4th dimension could be time, but it doesn't have to be. For example, going back to this thing with Google, if you have 1,000 employees and you have to collect 1,000 data points, that list of data points that you got, 1,000 data points, you can think of that as a single point, one point in 1,000-dimensional space. In 1,000-dimensional, because you have 1,000 coordinates. Yeah, you could do. So you could do different projections, but the main idea is that in higher dimensions, you still have the same distance formula. Is the Pythagorean theorem in n dimensions can describe, and when I say Pythagorean theorem in n dimensions, all I'm saying is like extend the same pattern of the regular Pythagorean theorem, and we can visualize it and understand it in 3 dimensions. And what you can kind of do is say, okay, well, if it's true in 3 dimensions, well, if I add another dimension that pops out of somehow the 3rd dimension, I could apply a similar argument to get it to follow it in the 4th dimension, and then do the same thing in the 5th and so forth. Pythagorean theorem in n dimension can describe how far apart lists of n coordinates are. How far, let me just do it this way. How far apart 2 points are in n-dimensional space. Okay. So, in other words, this can also tell us how far apart two lists of n numbers are. Okay, so now I'm going to ask you guys, and this is, I haven't told you yet, but I'm curious. Does anyone see, can anyone kind of volunteer an idea how this connects to standard deviation? It's not exactly, but it's
kind of taking the distance of every point from the average. So it's a distance calculation, and the squaring and square rooting is the absolute value thing.
Exactly. So we're not accounting for the denominator, but essentially, Quentin is exactly right. What we're doing is we have our list of 1,000 salaries at Google. So that's some point in 1,000 dimensional space. And we say, okay, how far away is that point from the point where everybody makes the same salary? That's the average point. So that's where person 1, person 2, person 1,000, they all make the same salary. And you're comparing, you're just finding the n-dimensional distance between those 2 points when you're squaring those numbers and adding them all together and taking the square root. And then you adjust that distance by the size of the square root of the, you divide out by square root of n, because you don't want to have you don't want to account for the fact that you want to kind of cancel out the fact that you have a lot of data points. So this allows you to sort of what we call normalize for the fact that you might want to compare distributions with different numbers of data points to understand how spread out they are. So what we're doing here is we're comparing, so in the standard deviation calculation, we are comparing essentially comparing how far away the point x1, x2, all the way to xn. This is a point in a 1,000 dimensional list of 1,000 numbers. Is just a fancy way a fancy way of saying is 1 point in a 1,000 dimensional space. How far is this point from the point where everybody has the same salary? And if everybody has the same salary, then your standard deviation is 0 because you're not, there's no deviation at all. Okay. These ideas of thinking about a collection of data as a point in a higher dimensional space is a very, very powerful idea in statistics. We're not going to really go into it too much beyond this idea, beyond this example. But what it allows you to do is it allows you to think about data in a more geometrical way. And it allows you to better understand things like clustering. Like one example is, your Netflix preferences, like what your Netflix history is. Maybe they see that, like, you could think of that as for each movie, you can give your rating or something. So maybe there's like 10,000 movies, and you've put like a 1 for you liked it, and a -1 if you didn't like it, or something like that. And that could be a single point in like a 10,000 dimensional space. And so what Netflix can do is it can visualize this space using different techniques, and it can find clusters of points that are close to each other. And of course, maybe you haven't watched exactly the same movies as somebody else, but it can kind of assume that, hey, we found that person A has similar, their distance is not far apart from another person in terms of their movie preferences are not far apart geometrically from another person's. Therefore, we can maybe recommend them this movie that the other person liked. And there's a high chance that they'll like it as well. That's kind of a very powerful approach to thinking about data and statistics. Okay, let's see. Yeah, that's standard deviation and distance. Let me kind of just finish off by saying, how do you find the standard deviation of a random variable? And what is the variance? So what we just talked about applied to samples, and we kind of we now also have a slight understanding, or an understanding that you can think of data geometrically in some ways. But now let's discuss random variables. So how to find the variance and standard deviation of a random variable. So let's just stick with the dice roll. Let x be equal to the dice roll. So again, we make our table. This is x, this is p of x. This is 1, 2, 3, 4, 5, 6. This is 1, 6. They all happen to be the same. So the variance of a random variable is defined as follows. The variance of a random variable x is defined as the expected value of x minus mu squared. And later I'll show you there's another formula for it as well. But mu is, just because the formula is going to get really messy if you write expectation inside of it. Mu is a shorthand for the average value of a random variable, or in other words, the expected value of x. And you can think of mu is very similar to sample standard deviation. Sorry, mu is similar to mu and x bar are similar, but they're, mu is you use or talk about mu when you're talking about something that you know the exact distribution of. You have full information. That's when you talk about mu. X bar is just when you take a set of data and you're trying to use that data to extrapolate to the entire population. And we'll talk about this either Thursday or next week. But they're very similar. This is the average value. So in this case, mu is equal to 3.5. So what you would do here is, if you think about what this formula does, is it's very similar to the thing underneath the square root in the standard deviation calculation. What you're going to do is you're going to take a new column and you just do x minus 3.5 and you just square it. So just like you do with standard deviation. So you get, this will be negative 2.5 squared. This would be negative 1.5 squared. This would be negative 0.5 squared. This would be 0.5 squared. This would be 1.5 squared. And this would be 2.5 squared. So you add them all together. And you also, because it's the expectation of some of this is a new random variable, you need to make sure you multiply each of these numbers by 1/6. So this is equal to the sum of xi minus mu squared times p of xi. And hopefully this expression looks really similar to the regular standard deviation. The only difference is, instead of dividing by, we don't have this n-1, we have this pxi. And in our case, pxi is equal to 1/6. It's equal to 1/6. So it's very similar, but you kind of adjust for your weighting yeah, it's the connection is very strong, except instead of n-1, you have this pxi. And you can imagine, like, if you have a data set where certain numbers repeat, you can kind of combine those repeated numbers, and that would give you like a almost exactly the same formula. Do you guys see how this formula is really similar to the earlier one? And then the standard deviation, which we call sigma, is just going to be the square root of the variance of x. So see if you can do a few examples where you actually calculate the variance of the standard deviation of some different random variables. And next class, I will show you another formula you can use to calculate. Actually, hang on. Next class, I will show you guys another formula you can use, and also how to set up this sort of calculation, because it's really tedious to do. You would essentially do negative 2.5 squared times 1/6, negative 1.5 squared times 1/6. You multiply these and add, multiply these, add, multiply these together, and do all those calculations. It's really tedious to do that, and you can set up a spreadsheet to calculate these. Yes, this was on Khan Academy, but I didn't go over it in the class. Okay, so we'll talk a little bit more about this next time, and then we'll move from this to talking about a little bit more about just regular statistics. This part of math is just part of probability, because there's no we're talking about probability distributions. So this discussion here is about probability. When we talked about collecting data, this discussion is about statistics, because we're assuming that we're taking a sample of data, not taking every data point from the entire population. And we'll elaborate on that further. But they're very, very similar, and hopefully you can see the similarities. Are there any questions on these ideas?
So if you do have every data point, do you get rid of the n-1 in standard deviation?
Yes, technically you would.
Okay.
That's right.
Could you explain the difference between the sort of average and mu again really quick?
Yes, okay, so I didn't want to actually discuss this today because
that's fine.
But it's really simple. And we're gonna I think I spent too much time on this anyhow in general in my classes. But a really important idea in stats is the distinction between a statistic versus a parameter. So in stats, and it's a simple idea, but it took me a while to actually appreciate it. In stats, you're always measuring, like you take a bunch of data and you measure something. And like, let's say you want to take the weight of, you want to figure out the average weight of a husky. So maybe you find 10 huskies and you weigh them, right? So the idea there is that you are trying to estimate some population parameter. And of course, it might be actually difficult to find, like, the important thing is that there is some overall population of huskies. Like if you were God, or some supercomputer, and you had infinite knowledge of the matrix or whatever, you could potentially weigh every husky that exists, either throughout all of time or at this moment, or whatever you want to set it up at, every husky in the universe, and you could weigh it, and you can get the true average weight of that husky, of the husky population. So that number exists, and that's what we call the parameter. And the statistic is the result of your data of the average from your sample. And the key difference is that the parameter is a true value. The true husky population average, that will, if you give me the definition of what the population is, that never changes. Like if it's the population at this moment in time, that's going to be, there's no randomness in that. That's just a number. But the statistic of the average of the sample, that changes based on which sample you picked. So that's the idea. X bar, when you actually see X bar, it's actually, and we'll talk about it in more depth in a few classes, but X bar is a random variable because it depends on what things you pick. But mu is not a random variable. Mu is a fixed number. And usually they're very close to each other.
So to be clear, mu is a parameter and X bar is a statistic?
Exactly.
Okay.
And S is also a statistic, but sigma is a parameter. It's very simple, but for some reason, either I was not paying attention to stats or something, but I missed this whole idea because it's kind of a subtle one, and it took me like again like a few years to realize, and it made it very, very confusing. But once you see it, I think it clears up a lot of the language of stats. Yes. All right, guys. I'll see you guys next time.
Thank you, Daniel.
Definitely. See you.
Thank you, Daniel.
See you guys. See you, Quentin.